Let's continue our discussion on micropump. So we will start talking about valveless micropump. Okay, valveless micropump will not use any valves, they will require nozzle diffuser arrangements to selectively transport fluid from the inlet to outlet by utilizing the difference between the pressure drop that happens across a nozzle to that across a diffuser. Okay. So this is a configuration of a valveless micropump that you see here, and what happens is when the membrane is trying to move up, as you can see here, then it creates a negative pressure inside the chamber, and so during that time, so this is the inlet. Okay, so this is the inlet and that is the outlet. So when the negative pressure is created here, the liquids move from the inlet into the chamber, also some liquid move from the outlet into the chamber. However, at the inlet we have a diffuser arrangement, and as we know that, and at the outlet we have a nozzle arrangement, and we know that the pressure drop across a diffuser is less as compared to that across a nozzle. So for that more fluid goes from the inlet to the chamber as compared to what goes from the outlet to the chamber. So we have more fluid coming from the inlet into the chamber. In the downward stroke, when the membrane goes down, this acts as a nozzle and this acts as a diffuser. So more fluid will go to the outlet than that will go to the inlet. So we have essentially net fluid going from the inlet to the outlet. So typically this is known as rectification efficiency, which we will discuss, and this is found to be maximum for a nozzle diffuser angle which is about 5 to 10 degree. Okay. So here we use nozzle diffuser arrangement. In valveless micropump we use nozzle diffuser arrangement instead of in place of valves. Okay. So the pressure loss across a nozzle diffuser, that is called rectification structures. So these are called rectification structures. Okay. So that means the flow has a directionality depending on the pressure drop across nozzle and diffuser. Okay. So the pressure drop across the rectification structure, pressure drop across the rectification structure delta P is given by Ji into rho U square over 2. Okay. So U is the flow velocity, rho is the density, and Ji is the pressure loss coefficient. Okay. And this pressure loss coefficient is going to be different for the nozzle and the diffuser. So we can define a parameter which is called the fluid diodicity, which is the ratio between pressure loss coefficients at nozzle to that at diffuser. Okay. So we define the fluid diodicity defined by the parameter eta f, which is given by Ji minus the pressure loss coefficient for the nozzle divided by pressure loss coefficient for the diffuser. Okay. So, eta f has a value typically between 1 to 5. Okay. So, definitely the pressure loss coefficient for nozzle is more, so that results in larger pressure drop across the nozzle. Okay. So, xi minus is the pressure loss coefficient, pressure loss coefficient across the nozzle. So, that is the negative flow direction. Okay. And xi plus is the pressure loss coefficient across the diffuser, which is the positive flow direction. So, we can write an expression for the flow rate can be written as Q is Q into delta V into F. F is the frequency of the oscillation of the membrane into square root of eta f minus 1 divided by square root of eta f plus 1. Eta f is the fluidic diodicity. So, that is how we can express the flow rate given by a valveless micropump in terms of the stroke volume and the frequency and the diodicity. Now, this parameter here is known as the rectification efficiency. Okay. So, for a pair of nozzle and diffuser, if the rectification efficiency is higher, meaning the difference between the pressure drop that happens for a nozzle and diffuser is more, then we would result in larger flow rate. Okay. So, the rectification efficiency is square root of eta f minus 1 divided by square root of eta f plus 1. Okay. Now, in case of valveless micropump, when it is not in operation, since we are not using any valve, there may be possibility of backflow. Okay. So, to prevent backflow, we use one way valve. Okay, upstream. Right. So, with that let us move on and talk about rotary micropumps. So, we talk about rotary micropumps. So, rotary micropumps have two gears which are driven in opposite to each other to drive very viscous fluids. Okay. So, rotary micropumps are used for driving viscous fluids, and because they handle viscous fluid, large torque is necessary. Okay. So, the rotary micropumps are suitable for highly viscous fluids, and so it requires high torque. Okay. So, we need external actuator. Okay. And the flow rate of such rotary pumps have been estimated. So, flow rate has been estimated, we can express in terms of a formula is H pi into N into d square minus by 2 minus c square by 2 minus mg square pi square divided by 6 into cos square phi. Okay. So, this is the expression for the flow rate. Here you can see d is the diameter of the gear, okay, and so this is the gear dia, and c is the distance between the centers of the two gears. Okay. So, c is the distance between the centers of two gears, and h is the channel height, so h is the channel height, and n is the RPM. Okay. So, mg is the diameter of the gear divided by number of teeth. Okay. So, n is the number of teeth, and phi is the pressure angle that is defined according to the geometry, the profile of the teeth, so pressure angle. So, knowing these parameters which are defined for a set of gears, and if you know the channel height and the RPM, we can calculate the flow rate of delivered by a rotary micropump. Now, because we are talking about viscous fluid, so the actuation is due to the external spinning motor. Okay. So, that is about the rotary micropump. Next we talk about centrifugal micropumps. So, the centrifugal micropumps work on the principle of the centrifugal force. Okay. So, normally the channels are carved on a typically a CD configuration, and by using the centrifugal force, this CD platform is rotated, and when it rotates, because of the centrifugal force, the liquid moves from the center of the CD to the outside, the perimeter of the CD. Okay. So, this is the configuration of a typical centrifugal micropump. So, this is the disc center about which the disc is rotated at a angular velocity of omega, and this is the liquid column that we are trying to analyze here. So, this liquid column, the bottom end is at a radius of r1 and the leading edge is at a radius of r2, and the average radius is r1 plus r2 by 2 is ra. So, this is r1 plus r2 divided by 2. So, for this liquid column, if this is rotated, there are two forces that are acting. One is the centrifugal force which acts outward, and the second one is the centrifugal the surface tension force which is trying to prevent this liquid column to escape. Okay. So, the flow is occurring in this direction from the center to the perimeter, and the surface tension is trying to prevent escape of this liquid column. Okay. So, we can write down the expression for the centrifugal force and surface tension force and equalize to determine the speed of rotation of the or the frequency of the rotation of the CD. Okay. So, here in this case the pump structure is on a CD platform, and the flow rate is controlled by the angular velocity of the CD, angular velocity of the disc. Okay. Here we can write down the expression for the centrifugal force. So, we write the expression for dFc over dr. So, how the centrifugal force is changing with radius. So, that would be rho omega square r into the area of cross section of the channel. So, this is basically the centrifugal force per radius. So, Fc is m v square over r. Okay. So, then we have dr here. So, that would take rho omega square r into area of cross section of the channel. Okay. So, here omega is the angular velocity and A is the cross sectional area of the channel. Okay. Similarly, we can write down the expression for surface tension force. So, the surface tension force Fs. So, surface tension force would depend on the surface tension coefficient into the weighted perimeter, okay, and that force directed towards the inside towards the center. Okay. So, typically if you have the profile something like this, and so this is the direction of surface tension. So, we are interested in this component. So, this is going to be rho cos theta, where theta is the contact angle. Okay. So, this we have already seen. So, this would be rho cos theta, and that rho cos theta is going to act on this weighted perimeter. Okay. So, the weighted perimeter is going to be pi dh. Okay. So, let us for now we call it L weighted. Okay. Now, if you balance surface tension with centrifugal force, the liquid is going to exit only when the centrifugal force is going to be more than the surface tension force. Okay. So, the liquid bursts out when the centrifugal force is greater than the surface tension force. So, for that to happen, we can write the expression for the centrifugal force from here. So, dr will get multiplied there. So, we call it delta r. So, delta r is nothing but the length of the liquid column. Okay. So, we have rho omega square r into A into delta r will be equal to rho cos theta into L weighted. Okay. So, now we substitute the values. Rho omega is 2 pi f. So, we have 2 pi f square into r is r a. So, this r is the location of the droplets. So, we call it average radius, and area of cross section of the channel is pi into dh square divided by 4 into delta r will be equal to L cos theta, sorry, rho cos theta into the weighted parameter, is pi into dH. Let us say dH is the hydraulic diameter of the channel, okay. Let us say dH is the hydraulic diameter of the channel, then from here we can predict what is going to be the burst frequency, okay. Fb is going to be sigma cos theta divided by pi square rho Ra into delta R into dH square. So, the burst frequency depends on the surface tension of the liquid channel interface, and it depends on the contact angle. It is inversely proportional to the density and the length of the liquid column, the average radius of the liquid column and the length of the liquid column and hydraulic diameter, okay. So, here we have W is the angular velocity, sigma is the surface tension, and L is the weighted perimeter, R A is R1 plus R2 divided by 2, and R is the radial coordinate, theta is the contact angle, and dH is the hydraulic dia. Okay. So, these are the different parameters. So, with that let us discuss ultrasonic micropump. Ultrasonic micropump are the mechanical type micropump, but they belong to the dynamic type micropumps. Okay. So, in case of ultrasonic micropump we do not have any moving part. So, what we do is we have a thin membrane and we have transducers on thin membrane coated with PZT materials, and these PZT materials are excited, okay, using the transducer. So, they generate what is called acoustic waves, okay. This is called flexural plate acoustic waves. Because of the movement of the acoustic waves we generated because of the vibration of the transducer, we generate a bulk motion of the fluid that is present on the surface of the membrane, okay. So, this is the ultrasonic pump. Okay. So, here we have this is the membrane we are talking about, this is the thin membrane coated with the electrodes, okay. And when the electrodes are excited, the membrane will undergo oscillation, okay. So, these mechanical waves will be travelling on the surface of the membrane, okay. So, when the mechanical waves will travel on the surface of the membrane, due to this the fluid that is present on the surface of the membrane will start to move in a certain direction, okay. So, this is the velocity profile that you see for the fluid that is present on the membrane. So, it will have non-zero velocity on the surface of the membrane because the membrane is always in a dynamic state, and so there are two parameters to define here, one is the acoustic evanescent length and the other one is the viscous evanescent length. The viscous evanescent length is the distance in the y direction from the surface of the membrane to a point where the velocity is maximum, okay. And the acoustic evanescent length is the distance between the point where the velocity is maximum to the point where the velocity in the bulk reduces to 0, okay. So, there are two important parameters here. So, we have this ultrasonic pump, it enables pumping without moving parts, and the pumping is caused by what is called acoustic streaming. Okay. And this is induced by the mechanical travelling waves, this is induced by mechanical travelling waves, okay, similar to that of a string. Okay. So, the mechanical wave, these mechanical waves are excited using interdigitated electrodes. Transducers placed on thin membrane. Okay. So, the velocity profile is characterized by two parameters, the velocity profile characterized by the acoustic evanescent length and the viscous evanescent length. The acoustic evanescent length, acoustic evanescent decay length, which is delta A, is given by the expression lambda divided by 2 pi square root of 1 minus u p divided by u b. Okay. So, here the lambda is the wavelength. Okay. So, when you have this flexural wave, this is the wavelength. Okay. Lambda is the wavelength, and up and us are the phase velocity and the sound speed. Okay. Right. So, up is the velocity of the phase, how at what speed this phase is travelling. Okay. Okay. And then we have the viscous evanescent decay length, viscous evanescent decay length, which is given by the expression nu divided by pi into f square root. Okay. So, here nu is the kinematic viscosity, and f is the frequency of the acoustic wave. Okay. Now, the acoustic streaming velocity ua can be determined as, so ua can be determined as, so this is the velocity of the liquid. Okay. So, the acoustic streaming velocity 5/4 into 2 pi f a square divided by up k delta a cube into 1 divided by k delta A plus k delta V into 1 minus T over 2 delta A square. Okay. So, that is the expression for the acoustic streaming velocity, okay, that we induce by the flexural waves. Okay. Here A is the wave amplitude, this A is the wave amplitude. So, we are talking about this amplitude here. Okay. And T is the plate thickness. So, the thickness of the flexural membrane, and K is known as wave number, which is 2 pi over the wavelength. Okay. This is called wave number. Okay. So, what we see here is that the acoustic velocity UA is varying as square of the amplitude, okay, the wave amplitude. Okay. So, what we observe here is the acoustic streaming velocity varies as the square of the amplitude, and this amplitude would depend on the configuration of the electrode. So, depending on the geometry of the interdigitated pairs of electrodes, the amplitude will vary. Okay. So, normally we use okay, in a conventional flexural plate wave, is called FPW, flexural plate wave. We have interdigitated electrodes, okay. So, on the surface of this membrane we would have interdigitated electrodes that will cause the acoustic waves, and let us say in a configuration we have the distance between. So, we have a configuration something like this. Okay. So, let us say this is the separation distance between the on one electrode is lambda, and between two pairs of electrodes is lambda by 2. Okay. So, if that is the case, so we have distance between the main and counter electrodes is lambda by 2, then in that case there would be a phase shift of 180 degree of the waves generated by these two electrode pairs. Okay. So, there would be a phase shift between waves generated by the two electrodes will be 180 degrees, and the acoustic streaming is going to be bidirectional. That means the acoustic streaming is going to happen in this way as well as in that way. So, the acoustic streaming is going to be bidirectional. So, the waves are going to go in both the directions, okay, and the resulting wave amplitude will be given by this expression. So, the A x t will be given by A0 over 2 into A0 is the maximum amplitude. So, it is sine 2 pi f into t minus k x plus sine 2 pi f into t minus 1 over 2 f minus k into x minus lambda by 2. Okay. So, that is the expression for the amplitude which we will be using in this equation to calculate the acoustic velocity. Okay. And in a case where this gap is lambda by 4 instead of lambda by 2, and let us say the electrode spacing is lambda by 4, then in that case the phase shift is going to be 90 degrees, and in that case the acoustic streaming will be unidirectional. So, the acoustic streaming will be unidirectional, it is going to be only in one direction, and we will have the expression for AXT, okay, which is A0 over 2 into sine 2 pi ft minus k x plus sine 2 pi f t minus 1 over 4 f minus k into x minus lambda by 4. So, this will be the expression for the amplitude if the electrode spacing will be lambda by 4. So, here in this case in place of lambda by 2 it will be lambda by 4, and in place of 2f it is going to be 4f. Okay. So, with that let us move on and talk about electro-hydrodynamic pumps. Okay. So, in electro-hydrodynamic pump it is a non-mechanical pump, and we use very high electric field to emit electrons from the emitter towards the collector, okay, and that ionizes the ions, the molecules present in the liquid, and since electrons are negatively charged, the molecules gain a negative charge and they migrate towards the collector electrode. So, in doing so they carry the bulk of the fluid, creating a pumping action. Okay. So, we look at EHD pumping, electro hydrodynamic pumping, which is different than electrokinetic pumping. Normally in electrokinetic pumping we use relatively lower voltage as compared to what you use in electrohydrodynamic pumping. Okay. So, this is the typical configuration of an electrohydrodynamic pump. So, there will be pairs of emitters and collectors. So, initially the liquid that is present between the emitter and collector may have some impurities. Okay. So, let us say there are some impurities present here in the liquid, meaning there are some already inbuilt charge inside the liquid. Now, if you apply a field between the emitter and collector, the positive ions will migrate towards the negative, this is the cathode or emitter. So, this is the cathode and this is the anode. Okay. So, this is plus minus, Okay. So, the positive ions will migrate towards the cathode and negative charges will migrate towards anode, and they will get electrically neutralized. Okay. So, this happens when the voltage is turned on and the voltage is relatively low, then charge neutralization in the impurity present in the liquid will happen. Then if the voltage is increased further to a high value, then what will happen is this emitter is going to emit electrons. Okay. So, electrons are going to be emitted from the surface of the emitter, and these electrons are going to interact with the molecules of the liquid, okay, and make it negatively charged. So, as you can see here, the electron is interacting with this molecule to make it negatively charged, and so now these molecules become negatively charged, and so they will migrate towards the anode. Okay. So, they migrate towards anode, in doing so they carry the bulk of the liquid with them, okay, because of the drag effect, and this is called the ion drag effect. So, the liquid movement or the pumping action is happening because of the drag that offered by the ions present in the liquid. Okay. So, here in this case we also call the ESD micropump, we call it as ion drag micropump. So, here we have the pumping between emitter and collector. So, pair of electrodes, and initially there may be some impurity present when voltage turned on, the impurities migrate towards opposite electrodes, okay, and this is going to be a short process, and they stop as soon as the charge gets neutralized. Okay. So, this process stops after the impurity ions get neutralized. Okay. And if you have voltage increased further, then and the electric field is greater than the threshold value, then we have emission of electrons from the emitter. Okay. And these electrons would attach to the molecules, attach to the liquid molecules, and so the molecule will get a negative charge. Okay. And these negative charged molecules migrate towards anode, Okay. So, they carry surrounding fluid, which is called ion drag effect. Okay. So, that is why it is known as ion drag micropump. So, as you can see here, the electrohydrodynamic micropump or ion drag micropump, the liquid moves from negative electrode towards positive electrode. Okay. Whereas, in case of electroosmosis, it depends on the movement, the direction of the pumping would depend on the zeta potential of the surface. Okay. So, we can say here in electroosmotic flow, the direction of pumping depends on the direction of electric field and the zeta potential of channel surface, whereas in ESD pumping the direction of pumping is from the negative electrode, which is also known as the emitter, towards the positive electrode, okay, or known as the collector. Okay. So, with that discussion we will move on and talk about electrokinetic micropump. We have already covered the electrokinetic micropump when we were talking about electroosmosis, but here we will consider an example problem and try to design the microfluidic circuit for a combination of where we talk about electroosmotic pumping with capillary electrophoresis. Okay. So, we will continue our discussion on in the next lecture. So, with that let us stop here.